we have the following circuit. Essentially, what we have is, in total, we have 4 resistors and 2 batteries. Now, we want to find the current in each loop. This type of question is going to involve us having to solve a system of 3 equations. One equation we're going to be using is the junction rule. The other 2 equations will come from using the loop rule, as I've drawn here and here. And the junction I'm going to focus on is this one in particular. Now, the currents can be drawn in any direction in a circuit. The reason is that, let's say you draw all the currents flowing in, though they're not supposed to. I know that logically at least one of these currents, whether it's I1 or I3 or I2, has to flow out of the junction. So like this way or this way. But even if I do draw them, all of them flowing into the junction, when I actually solve for their individual values, I'll get a negative sign in for some of these currents, and that negative sign is going to tell me that this current was actually flowing in the opposite direction. So let's say I get negative 5 amperes for I1. That would mean that I1 wasn't flowing as I had assumed. It wasn't flowing in this direction, but it's actually flowing in the opposite direction, so downwards. So that kind of automatically, once you get the answer, it'll automatically correct your assumption. Even if you get a negative answer for the current, it doesn't mean that it's wrong. Your teacher will still likely accept it. It's not an issue. So now to actually start solving the question, the first thing I'm going to do is I'm going to combine R3 and R4 since they're in series. And how do we know that these 2 resistors are in series? We know that because the same current is flowing through each of these resistors. I3 is flowing here, and I3 is also flowing over here. So it's that simple. So because of that, I'll use a different color. Maybe I'll use a bit of a thicker font, and I'll add them in series. I'll just say that there's one resistor in this loop, and the purpose, I'll call it R34. And so when I add resistances for resistors that are in series, I add them directly. So it's going to be R3 plus R4, the resistance in R3 plus the resistance in R4, which is going to give me 7 ohms. Now I'm going to erase this because I'll need more space to come up with the other equations. So the first equation I'll use is the junction rule. I'll make my font a bit smaller. So I'm focusing on this junction here. Again, you could have also focused on this junction here. It doesn't really matter. It will give you the same result regardless at the very end. Now, I know that the junction rule states that the sum of the currents going into a junction are equal to the sum of the currents leaving a junction. In this case, all of my currents are flowing into the junction. So I1 plus I2, that's at least how I've assumed. That's what I've assumed that they're doing. I've assumed that they're all flowing into the junction, which is not going to be true, of course, logically. Now, since I know that either one of these currents is going to be negative, so that I'll get a 0 on this side of the equation, since I've assumed that there are no currents flowing out. Now what I'll do is I'll rearrange this equation for I1 just so I can solve it more easily with a system of 3 equations. Now I'm going to erase some of this. My second equation is going to be the following. I'll do a loop here. So I start here, I go through V1, and that's the part of the battery that's longer is the one that represents the positive terminal, and the part of the battery that is shorter is the one that represents the negative terminal of the battery. So I'm going through a voltage of 24 volts, which I'm just going to call V1 for now. And then I'm going through R1, which is 3 ohms. And I'm going from high to low potential. I've assumed that this is the current direction, so low minus high, or final minus initial, which is going to give me a negative answer, is going to be negative I1 R1, because the current flowing through the circuit is still I1 for now. Now when I move down all the way here to R2, the current is going to be different. It's going to be I2. But I am moving against I2. I'm moving against what I've assumed. So the current I2 is flowing from high to low potential, but I'm going from low to high because of the loop rule, how I'm using it. So final minus initial here will give me a positive sign. And it's going to be positive I2 times R2. And now when I come down here, I've basically completed my loop. So this is equal to 0. The sum of the differences in potential across a closed loop always equal to 0. That is the theory behind this loop rule. Now I'll do the same thing for the other loop here. Pay attention to the red part of the loop. We only have one resistor. I've condensed it down to make the loop rule easier. So I'll start from this end. I'll go through V2. Actually, no, sorry. The way I've drawn, I'm going this way. There we go. So I'll start here and I'll go this way. So that's the positive terminal of the battery because that's the longer terminal. So I'm going through a potential difference of 29 volts. I'll just call it V2 for now. Then I'm going through high to low, final minus initial, so that's going to give me a negative answer. A negative I3, that's the current, times R34, which is, furthermore, I'll move through the R2 again, and the current is going to change. It's going to be I2, so it's going to be negative I2 times R2, and again all of this will be equal to 0 because I've completed the loop. So now to solve the system of 3 equations, something I have to mention is that I'm showing you how my teacher solved it in class. I won't be able to explain why we solved the system of 3 equations the way we do. This is something you can ask your teacher. You can ask them, how do we actually solve a system of 3 equations in the quickest and fastest way possible, especially in the case of a test. If a teacher gives you a question like this, the troubling part is most likely going to be the system of 3 equations itself, not necessarily applying the different Kirchhoff's rules. And yeah, so I won't be able to explain why it is the way it is. So we'll start with equation 1. We're going to plug it into equation 2. I'm going to substitute equation 1 into equation 2. Specifically, I1 matches I1 here. So this is where I'm going to put equation 1. And then I'm going to multiply it with R1, essentially. So when I do that, what happens is the following. I'll rearrange v1 onto the other side. So I'll have negative for I1 instead. I'll have I2 minus I3 times R1 plus I2 R2, which is equal to negative v1 because it said I'll move it to the other side. Now I'll expand. So I have positive I2 times R1 because I'm multiplying R1 in. And then I have also positive I3 times R1. And I also have positive I2 times R2, which is equal to negative V1. Now I'll be rearranging for I3. So I3 R1 is equal to negative V1, negative I2 R1, negative I2 R2. I3 is equal to negative V1 minus negative I2 R1 minus I2 R2 divided by R1. I'll simplify this equation a little bit more. I3 is equal to negative V1. I'm going to factor out, I'll factor out negative I2. And what that's going to do is give me positive R1 and positive R2. So I'm factoring out I2 from these two pieces of this larger equation. And what I'm going to get is negative V1 over R1 and minus I2 R1 plus R2 over R1. So I'll have to erase a bit now. This is a new equation we got. I'm going to just leave a slight color coding here. Now, with this equation, so basically what I've done is I plugged equation 1 into equation 2. Then from there I sort of rearranged for, I believe it was I3. That's what I've done so far. Now I will plug I3, this equation I have, into the third equation, and I'll rearrange for I2. So when I plug this guy into this guy, this is what I'll get. I'll get V2 minus V1 over R1. So what I'm going to do is I'm going to kind of break this equation up a bit, and it is possible to do this. There's nothing algebraically wrong with writing it this way rather than that way. Minus I2 times R1 plus R2 over R1. Now this was for I3. So we have this multiplied by R3, 4. And we have plus I2 R2, which is equal to 0. So now we get this massive equation and we expand it further. So we have V2 plus, because minus times minus is plus, V1 over R1 times R3, 4, because I'm distributing it inside the brackets. Again, plus I2 times R1 plus R2 over R1 times R3, 4. Again, I'm distributing it into the brackets. Plus I2 R2. Now, the reason behind why we had to do all of these steps is so that we can try to just get to one current in the equation. So now that we have just one unknown, we can isolate it by factoring it out of the like terms, and we can finally find its value, and then we can plug it back into, this equation or any one of these equations to find the other second current, and then we just use this equation to find the third one. So again, the meat of these types of problems is just knowing how to solve the system of equations. You can perhaps try to find a YouTube video on how to solve a system of 3 equations. That could help you understand how to solve these for a test scenario. Now I'll continue with the problem. So I'll rearrange for I2 by factoring it out. So what I'll be doing is I'll be moving these two terms onto the other side of the equation, so all the way there. And I'll have to erase a bit so I can give myself some space. So I'll factor out I2 as well, because it's the common term among these two, the common variable among these two terms. That's what I meant. So when I factor out I2, I get R1 plus R2 over R1 times R34 plus R2. All of that, which is equal to minus V2 minus V1 R34 over R1. And then I'll divide. Now instead of dividing, like, I have all my values for the resistances. I have all of these values. So instead of like dividing by all these variables that are just going to confuse me, I'm just going to start simplifying things by putting in the numbers and just adding them up, and then just dividing by a number here. It's just easier now. I had to use these variables before because there was a purpose behind them to help us find the right equations, but now you don't need to care too much. You can plug in the numbers. So I'm not gonna plug in the numbers and show them to you like by writing, but I will plug them into my calculator and simplify them a bit. So I believe I'll start with this piece here. I'll try to simplify it by adding up the numbers. So R1 was 3 ohms, so 3 ohms plus R2, which is 3 ohms as well, and I divide that by R1, so which is 3 ohms again, so I get 2. And that 2 is being multiplied by R34, so I'm going to multiply it by 7. That's what R34 was, and I'll get a value of 14 plus R2, which is 3 ohms again, so that's going to be 17 ohms times I2, which is equal to negative V2, which is negative 29, minus V1 times R34. V1 is 24 times R34, which is 7 ohms, and divided by R1. R1 is 3 ohms. So when I do this, I get negative 85 on this side. Now I rearrange for I2, and negative 85 divided by 17, and I get negative 5 amperes as the current for I2. Now again, what I mentioned previously earlier on is that when you get a negative value, it just means your current was actually flowing in the opposite direction. So I assumed my current was flowing up, but it was actually flowing down. Does that make my answer wrong? Of course not. My answer isn't wrong. My teacher will still accept it as long as I stick to that assumption, which I will. My teacher will still accept it. It's not an issue. With these kinds of questions, you have to start by assuming something. So your teacher can't deduct marks for something like that, because you have to assume the direction of the current at the beginning. It's just a fact for these kinds of questions. So the red arrows are just there to say that this was where it was actually flowing. So that kind of agrees with Kirchhoff's junction rule. So I have I2, that's awesome. Now I'll find I1. So what I'm going to do is I'm going to just take this equation and rearrange it for I1. But I'm just going to do this like, I have all the numbers now, so I'm just going to plug it into my calculator and give you the value directly. So I1 is equal to I2 times R2. I2 is negative 5 amperes. And yes, you keep the negative sign. I2 is negative 5 amperes times R2. R2 is 3 ohms. So I get negative 15 for this term. And then I have V1, which is 29 volts. So I do 29 plus minus 15, which gives me 14. Now I move 14 to the other side, so it becomes negative 14. And I divide by negative R1. Negative R1, which is 3 ohms. That gives me a current of negative 4.67 amperes. I'm rounding this up for I1. Actually, I've made a bit of a mistake with this question. My value for I2 is correct. My value for I1 and I3 is wrong. And here's why. I chose to find I1 using this equation here, and I shouldn't have done that. Basically, when I was solving this question later on, I managed to create this equation, and I should be, now that I have I2, I should be solving for I3 first using this specific equation, not this equation. The reason behind that is because I can't explain it to you clearly. I don't understand it myself, to be honest, but when you plug certain equations into each other, this equation has something new about this circuit inside of it. Like, this equation considers something that one of these equations is not considering on its own. So like, one of these equations has forgotten something. This is just an analogy I'm using to perhaps help you understand it a bit more. So when we when we substituted and rearranged for I3, this new equation considers something about the circuit that wasn't in any of these equations before. So that's why after solving for I2, we use this equation to get I3, and then we use that equation to get us the I1. We never, after having solved for I2, use the equations we started with. Never. So I have I2, and now I'll use this blue equation to give me my value for I3. So I'm just going to directly plug this into my calculator. This is going to give me minus 24 minus I2 would be negative 5. And yes, you include the negative sign, times R1 plus R2, which is 3 plus 3, which is 6, divided by R1. R1 is 3 ohms, and we get 2 amperes for I3. Positive 2 amperes for I3. So it still makes sense. Like, I3 is flowing into the junction and I2 is flowing out. Let's see what happens with I1. I1 is equal to negative I2 minus I3. Now we go back to using this original equation. So I1 is equal to negative I2 minus I3, so that's going to be negative I2, which is negative 5 amperes, and then minus I3, which is 2 amperes. And this is going to give me a value of positive 5 minus 2, which is positive 3 amperes. So the directions I got for I3 and the directions I got for I1, the directions I assumed for I3 and the directions I assumed for I1 were indeed correct. So I1 is indeed flowing this way, and I3 is indeed flowing that way. Even if you get a negative answer here, it's not a problem. Your teacher will still accept it. Again, with these questions, you have to always start with assuming the direction of the current. So yeah, this is the slight correction I had to show. We have our currents here, and they add up. Negative 5 amperes is equal to 3 amperes plus 2 amperes, which is positive 5 amperes. Sorry, no. Basically, 0 is equal to minus 5 amperes plus 5 amperes, and the plus 5 amperes comes from 2 amperes plus 3 amperes, like that. I hope this helps.